These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There is a link to my website in the info box. The address is www.freelance-teacher.com/videos.htm, or you can just use the link in the info box. By the way, I also offer tutoring via Skype, and you can find more information about that Skype tutoring service at my website. Thanks. Relativity was a while ago. I don't even remember. Did you and I work on relativity together?
Yeah.
We did? Okay.
Yeah.
Well, why don't you tell me then, did you have any ideas about how to get started on this?
Well, we used that formula. I forgot how to figure out which one's L, like the rest time and the
Okay.
other time.
So our basic formula here is okay, so here's our basic formulas for the relativity of length and time. Do you remember what does C stand for?
Speed of light.
Right. Now you can see here that one of the important, so what this is telling us is that different observers will measure different lengths, and different observers will measure different times. Different observers will measure different lengths, and different observers will measure different times. Now, when is relativity important and when is it not important? When would relativity be important here, and when are things not very relative?
When V is small.
Now, when V is small, is that when relativity is important or it's not?
When it's not.
So when V is small, do different observers measure the same lengths and times or different?
The same.
Yeah. Good, that's right. Well, you can see that from these formulas here, because if V is much smaller than C, what happens to this term here?
Goes to 0.
And then these are about the same thing. Okay, so relativity is only important when V is pretty close to C, because then this term is pretty big and it makes a difference when you subtract it from 1. All right, so that's an important point right there when the relativity matters. So it seems like the important thing is the ratio between V and C. The important thing is the ratio between V and C. So as you might have already seen if you looked at the answer key here, in this problem they invented this symbol for that, which he called the speed parameter, beta. Now when you and I were working on these problems together, we didn't actually talk about beta. The homework didn't talk about a speed parameter, but I guess the speed parameter is this ratio of V to C. You can see why that's a useful variable. So let's rewrite the equation. What would the equation be in terms of beta?
L times root 1 minus V squared.
Beta squared. Good. And how about the time equation?
T equals T times root 1 minus V squared. Wait, is B always V over C? Is that like a...
That's just the definition
Okay.
of beta for relativity. The definition of beta, so here the speed parameter beta is defined as V over C. So when is relativity important in terms of beta? What does beta have to be for relativity to be important or unimportant?
When it's little, or it's 0, it's not important.
Right. And so what would beta be when relativity is important?
1?
Close to 1.
Yeah.
Just slightly less than 1, basically. Because remember that except for light, nothing goes at the speed of light. So this is generally going to be a little less than 1, but it might be close to 1, and then relativity is important because when beta is pretty close to 1, it makes a big difference when you subtract it over here. Okay, so that gives us a slightly easier way to look at the equation. Now, when we talked about relativity last time, we saw maybe the hardest part about dealing with relativity is just to figure out who gets the L prime and who gets the L, or who gets the T prime and who gets the T. If you can just figure out who to plug in for the prime and the non-prime, maybe you can just plug and chug in the problem. Well, which is smaller, the prime or the non-prime?
The non-prime. Well, wait, no,
Take your time. You can work that out on paper if you need to. And here we just want to figure out which is smaller just based on the math, not on the science. Mathematically, who does this equation say is smaller? You might need to work that out on paper.
L is smaller.
So you're saying this one is smaller, right?
Yeah.
Okay, well, let's think about that. So what can we say about this square root? I think you're already on the right track with that. Is that square root bigger than 1 or less than 1?
Less than 1.
So basically this is a fraction. This is a fraction.
Yeah.
Well, so we're multiplying L by a fraction to find L prime.
Wait, L is bigger.
L is the bigger one?
Yeah.
Because you have to multiply it by a fraction to find L prime. What this is telling us is that L prime is a fraction of L. A fraction like 1/3 or 1/2 or 1/4. Okay, so to review, which of the two variables is smaller?
L prime.
Which one?
L prime.
Yeah, L prime is smaller. And the non-prime is bigger. And again, that's something if we forgot it, it should be pretty clear from the math here. For example, if you just looked at this equation here, say, I think it should be pretty clear that this means that L prime is 1/3 of L. That means that L prime is less than L. Well, that's basically what this equation says. It's saying that L prime is a fraction times L. So L must be the bigger number. Okay. It turns out that even though this seems trivial, this is really the key to solving most of the relativity problems you'll see. The key is just knowing which of these variables is bigger and which is smaller. Well, who's bigger, T or T prime?
T.
And why, how do you know?
This is the same as.
That's an important idea. The equations take the same form. So again, we're taking T and multiplying it by a fraction to get T prime, so T prime is a fraction of T. Okay. Of course, if beta was close to 0, then T prime would only be a little bit smaller than T. And if beta was close to 0, then L prime would only be a tiny bit smaller than L, so small that you probably couldn't even tell the difference. Remember that what this is saying is that different people will measure different lengths. Well, that again should strike you as really weird because in ordinary life, different people measure the same lengths. For example, if there's a car going by and you measure the length of the car, the people inside the car would measure the same length. Or things don't seem to necessarily change size just because they're moving relative to each other in normal life. Or by the same token, I think we used this example last time, if there's people on a plane watching an episode of Seinfeld, to them it seems to take about 30 minutes, and if you're watching from the outside through a telescope, to you it also would seem to take about 30 minutes. It seems like everyone measures the same time, but that's only because the plane isn't going fast enough. If the plane was really going very quickly, then to you on the outside, it would seem like the Seinfeld episode was taking a lot longer than 30 minutes. So relativity really is quite weird because it says that different people measure different times and lengths, but this only happens when things are moving very quickly relative to each other. Okay, so we need to focus on who's smaller and who's bigger here. All right, and now if we keep that in mind, that's really all we need to answer parts A and B. A and B are actually very simple relativity questions. Maybe after we finish these, we can go over some more concepts that you might need for a harder problem. But all what we've just talked about is good enough for this. So let's try part A here. Again, how would you attack part A?
So the length is 1/4 its rest length.
Mm-hmm.
So L prime is smaller.
Mm-hmm. This is something you probably have to work out on paper rather than in your head. Let's see. How did you come up with that?
Because a length is 1/4 its rest length.
Now, how do you know that this is the one that stands for the rest length?
Oh, I thought L naught was always the rest.
Let's see. Okay, yeah, I think that's generally true. How would you know that if you forgot that? So in this case, which is bigger? Is the rest length the bigger or the smaller based on what they said in the problem?
Bigger.
Yeah, how do you know? Because they said that the length is 1/4 of the rest length. That means the rest length must be bigger. Well, who stands for the bigger variable, L or L prime?
L.
Okay, so even if you've never heard of relativity and rest lengths before, just from looking at this equation, you would be able to say to yourself, well, gee, they told me that the rest length is bigger, and I know the bigger variable has to be L.